calculations. So since our image is read in an array format inside our computer, so we need to deal with images, right? We need to deal in order to deal with images, we need to deal with array, right? So firstly, we should learn how to manipulate arrays. So let's just quickly go through NumPy so that we have a fair enough idea like how to deal with arrays. So is my screen visible?
Yes, yes,
Yes, Soumya.
Yeah, great. So here are a few functions. Firstly, you need to import NumPy. So here we are importing NumPy as NP. NumPy array, it's a yeah. So here we are declaring a 2D array, NumPy array inside the variable a. So 1, 2, 3. This is the first element of this 2D array, and 4, 5, 6 is the second element. So if you print a, then you can see that a 2D array is printed here. And since it is a 2D array, two-dimensional array, so the dimensions of this array is 2. So at the name of the array followed by ndim, it will print the dimensions in that array, which is 2. Next is the item size, a dot item size. So the size which each element of this array consumes, that item size will return it. So as you can see that each element of this array is an integer, right? And here like in my laptop it's a 4-byte integer. So 4 is returned here, which shows that each element consumes 4 byte in this array. And d type is the data type of each element. So in 32, that is the data type of each element of my array. Next is a dot size. So a dot size, it basically returns the total number of elements. So like in this array there are 2 arrays and each array has 3 elements. So in total there are 6 elements, and that is what this a dot size returns. Next is a dot shape. So a dot shape returns. Uh, is somebody saying something?
No, Soumya, you continue.
Okay. Next is a dot shape. So a dot shape returns me the shape of my array. So here are 2 rows and 3 columns. So 2 by 3 is the shape of this array. That is you can see here 2, 3. That's a tuple returned by a dot shape. Next is a dot sum. So it's like evident, it's going to sum over all of these elements and then it returns the sum. Now this is important, x is equal to 0 and x is equal to 1. Like if you don't pass this argument of axis and simply do a dot sum, then it just sums over all of the elements. But when you pass the argument x is equal to 0 or x is equal to 1, then what happens? See, x is equal to 0, you can consider it as the downward axis, and x is equal to 1, it is the direction, it is the horizontal direction. So when we sum in the direction of x is equal to 0, that is in the downward direction, then it's just you can see that elements are added in the downward direction. So here 1 plus 4, it will add up to 5, 2 plus 5 will add up to 7, and 3 plus 6, it will add up to 9. So 5, 7, 9. This is an array you can see. And next is when you sum in the direction of x is equal to 1. So that is you sum in the horizontal direction, like in towards the right direction you can see. So 1 plus 2 plus 3, that is 6, and 4 plus 5 plus 6, that is 15. So this you can see like 6 comma 15, that is the result when you sum in the direction of one axis. Yeah. So like axis wise summation also you can do like this. Next is multiplying the array with some constant. So this is what it does is it multiplies each element of your array with that given constant. So you can see that here 1, 2, 3, 4, 5, 6, and each element here is multiplied, it's by 3. Next is np dot square root a. So it just computes the square root of every element and returns that array. A dot min and a dot max. This will return the minimum and maximum element in your array. Next is np dot mean of a. So it just calculates the mean value of all the elements. Next is slicing. it's a bit important. So here what we do is, see, first you need to know about indexing. So like yeah, this is my array. There are two elements in it. First, this is it's a 1D array, 1 2 3. This is my first element, and 4 5 6, this is my second element. So here indexing starts from 0. So I can call that this array 1 2 3, it is the 0th element of my array, and 4 5 6, it's the first element or 1th element, you can say, of my array. Okay, and inside this element, again my indexing starts from 0, and this one over here, it's the 0th element. 2 over here, it's the one element, and 3, it's the second element. Similarly, inside this element, 4 is at index 0, 5 is at index 1, and 6 is at index 2. Okay, so like I can do slicing over here. Yeah, here it is. So this column represents like from which index to which index you want your elements to get listed. So, and one more thing, that the number or argument after colon is excluded. So suppose I write here from 0 to 1, then 1 is excluded here. So only the element at 0th index will get printed. So suppose if I had written 0 colon 2 over here, then only the elements at 0 and 1 will get printed. Okay, so currently 0 colon 1 is written here. So only the 0th element will be printed. So 0th element is the first array, that is 1, 2 and 3. Okay, now inside this array itself, you can do slicing. So for that, you just put a comma over here and again do slicing like 1 comma 2. So 1 comma 2 means the element at index 1 will be returned and 2 is excluded. So only the 1th element will be returned. And inside this array, the element at index 1 is 2. So overall, this whole expression will return me 2. Here I am declaring another array np dot. This is another 2D array, and it has the same dimension, same shape as the as that A array, or the array A. So like both of them are 2 by 3 arrays. Like this is my array B and this is my array A. So if I write A plus B, then it's going to do element wise summation of both of them. And then A star B, it's going to multiply them element wise. So it's not a usual matrix multiplication. What it does is, since both of the arrays are of same shape, it just takes the corresponding elements and multiplies them and then returns the array. So it's like 7 times 1, 7, 8 times 2, 16, 9 times 3, 27, like this. Next is a reshape function. So I have this array B, and you can see there are 6 elements inside it, and 6 elements can be reshaped in any form, like 2 by 3, 3 by 2, 1 by 6, 6 by 1. These are the possible ways in which you can arrange 6 elements, right? So inside this reshape function, you need to pass like in what manner you need to arrange or organize these 6 values. And if you pass any other value now, then it will throw an error, because 6 elements cannot be organized in any other manner other than 3 comma 2, 2 comma 3, 1 comma 6 and 6 comma 1. So here I passed 3 comma 2. So what it does is, it just takes all these 6 elements in the same sequence and just reshapes them in like in 3 rows and 2 columns, and the order is retained here. Next is Ravel function and Flatten function. Both the functions essentially performs the same. They are essentially same. What they do is, they simply take all the elements of my array. Yes.
Can you please explain the reshape again? Means does it take all the 6 in means that is take means all the elements of all the arrays, and then it divide into 2?
Which function you want me to explain?
Reshape.
Okay, reshape function. See, there are 6 elements in my array B. Okay, so
Yeah.
6 elements can be arranged either in 6 by 1, 1 by 6, 3 by 2 or 2 by 3. Like
Yes.
either you can have 3 columns, 2 rows, 2 columns, 3 rows, 1 column, 6 rows, or 6 column, 1 row, right? So out of these 4 options only, you need to pass any one of the option. So I passed in 3 comma 2. So what it does is it tries to reshape my array in such a manner so that there are 3 rows and 2 columns. Okay, and the sequence is maintained. So like earlier my array was 7, 8, 9, 10, 11, 12. So you simply just write these elements in the same order: 7, 8, 9, 10, 11, 12. But you need to keep in mind that the shape of this array should be such that there are 2 columns and 3 rows, and the sequence is maintained: 7, 8, 9, 10, and 11, 12.
If we want to exchange 7 with 9 and 9 with 7, then
Then you need to introduce another array because it's not the same array, na?
yes, I got.
Uh, okay. Yeah, Ravel and Flatter function, they basically just take all the elements in the same sequence and jot them in a single line. It flattens the array basically. Next is np.zeros function and np.ones function. So here again you need to pass the shape of your array. So like I passed 2 comma 3. So what it does is it generates an numpy array of 2 rows and 3 columns, and each of its element is 0. np.ones also does the same thing, just the difference is each of its element is 1. So here I passed in 3 comma 4. So it's a 3 by 4 numpy array and each of its element is 1. Next is identity matrix. It's the same matrix which you study in your plus 2. So it's a 2D square matrix, right? So here you don't need to pass 2 arguments, just a single integer which is the side of my square. That should be passed here. So here I passed 3. So a 3 by 3 square matrix is printed here and it's an identity matrix, as you can see. Next is np.arange and np.linspace function. See, these are a bit important. Just focus. See, my first 2 arguments, 1 and 10. So basically I need some elements or some numbers which lie between 1 and 10, beginning from 1, ending at 10. And what this 2 represents is that the gap between any 2 consecutive numbers should be 2. So like I start with 1 and with a gap of 2 I move forward 1, then with a gap plus 2 3, plus 2 5, plus 2 7, like this until I reach 10, or until these numbers are less than or equal to 10. Okay, and in the linspace function you don't pass this gap. Instead you pass like how many elements between 1 and 20 do I want, and the gap between any 2 consecutive numbers, it's decided by this function itself. Like the function itself will decide that what should be the gap between any 2 consecutive numbers. So like here I passed 5, so it will choose, or it will calculate 5 equally spaced elements between 1 and 20, and what should be the gap between any 2 consecutive elements, it will calculate on its own. So this was all about basics of NumPy before you start with OpenCV. So any doubt in it?
This is the last function. Can you please explain that linspace?
Okay, linspace function. See, my first 2 arguments are 1 and 20. So I need some elements between 1 and 20. So it just returns me an array with some elements which are in increasing order between 1 and 20. But this 5 tells me that I need 5 elements between 1 and 20, and these 5 elements should be equally spaced. So as you can see that the difference between any 2 consecutive elements is same over here. Okay, and what should be the difference between them, that this function calculates automatically. So like I want 5 equally spaced elements between 1 and 20. So this linspace function just returns me that array with 5 elements in it.
Okay, got it.
Okay, so next let's move forward with OpenCV.
Excuse me, Didi.
Yes.
Didi, Ravel and Flatten both have exactly the same function.
Yeah, like you can see here that Ravel, when you apply this function Ravel to the array, then it just takes all the elements and puts them in single row. And if you just need, nitty gritty details about each and every function, like what are the optional arguments or what more a function can do, like then you can refer the documentation. So there, what they do is they clearly explain like in each function or required arguments, optional arguments, every nitty gritty details about each function is mentioned there.
Okay, thank you.
Okay, so yeah, next with OpenCV. Okay, so yeah, suppose you have an image and you want to deal with that image, like you want your computer to read that image and do some processing on it. So how do we do that actually? So suppose you have an input image, okay, but this is how humans see this image, right? But when you pass this image to a computer, then how it reads it is it converts it into a digital form, like some numbers in a array, okay. And then obviously you cannot manipulate directly this image. To manipulate or to do some analysis, computer needs some numbers, right? So because it knows how to deal with binary things, so image, to convert an image into binary, we first convert it into digits or numbers, and then these numbers are read in a binary format, right? Because computer knows like how to deal with zeros and ones only, right? So you cannot directly manipulate this image. Firstly convert it into digital form, then do some manipulations on it or play with these numbers, and then it spits the final output. So what is OpenCV? OpenCV, it's an image processing library and it's available for C, C++ and Python, but today we'll be looking at only for Python. Okay, so firstly, like it's you need to install OpenCV in your local machine, because in general it does not come already with your machine. So you need to install it manually, and for that just go to your terminal and type pip install OpenCV Python. Yeah, pip, then space install, then opencv hyphen python, everything in small letters. So just try it in your terminal and it will get installed automatically. So after that, like in any IDE, if you if you try to import OpenCV, then it will easily get imported. And if you face any error while installing it, then do reach us. So next, let's just study images a little bit. So like as you can see, like this is my original image over here, and as you zoom into it, no, like first you zoom it a little bit, then you zoom it more, and again see that the image starts to burst out. You can see like you cannot zoom it more because its quality starts reducing. Why? Because it consists of pixels, very small square pixels, and as you zoom in it now, then these pixels start to expand, and you can see that each of these pixels you can see clearly. uh, so it shows that my image is basically a 2 by 2 grid of these square pixels, and inside any single pixel the color is same at every point. So like if I zoom into it now, you can see that all of these pixels are different, but inside any single pixel the color is same everywhere. Okay, so that is the property of a pixel, that the color at each point in that pixel is same everywhere, and these pixels are arranged in a 2 by 2 grid, and this is what constitutes your image. So while reading an image, na, your computer needs to read these pixels. So there are three types of images. First is binary image, then grayscale image, and an Rgb image. Binary images basically have two types of pixels, either white or black. So the value of the pixel is either 0 or 1. The pixel is either switched off or switched on. Switched off pixel means it has a value of 0 and the color is black. And switched on pixel has a value of 1 and it's white in color. So like here you can see it's a binary image, because if you pick up any pixel, it's either white or black. Second is a grayscale image. Inside a grayscale image, the value of like any pixel, it's either black or white or it has any shade of gray. So when you pick any pixel, it's basically a shade of gray. And third is your RGB image. RGB images are the general images that we deal with, which are colored images. So they have some red component, some green component, and some blue component in it. Now, how an image is read by OpenCV. So we just saw that an image is constituted of a lot of pixels. Okay, so an image is stored as a NumPy array inside OpenCV, and the dimensions of that array is like the number of pixel rows times the number of pixel columns times the number of channels. This number of channels that we will see later, but number of pixel rows and pixel columns, that is like you can see that in that NumPy array, every element in that NumPy array corresponds to a pixel in my image. Okay, so suppose like I have an image and there are 512 by 512 pixels in it. So basically when OpenCV reads it, then it just generates a NumPy array of 512 by 512 elements in it, and each element corresponds to a pixel in my image. Okay. And the value of that element in my array, it is the intensity of my pixel in that image. Okay. And each element of the array contains the value of this intensity at the corresponding pixel. So yeah, suppose like I need to read this image, so it constitutes of a lot of pixels, right? And suppose I pick a pixel in this region, and you can see that its intensity is very high because it's white in color. So here our intensity values range from 0 to 255. So 255 means the highest intensity, that is very white, and 0 means lowest intensity, that is black. Okay, so if a pixel is very bright, very light and white in color, then its intensity is very high and the value in its NumPy array is closer to 255. And if it's black in color, then the value is closer to 0. So like you can see here, it's my binary image, like it's written in a white background. It's a binary image because the pixels are either black or white. Okay. So 0 means that this pixel is switched off, and 1 means that this pixel is switched on. And like you can see that this image is divided into a lot of pixels, 2D pixels, and the same thing you can use while generating a NumPy array out of it. So like there are pixels horizontally and vertically, just generate a NumPy array out of it, and if there is any white pixel, then write the value 255. If there is any black pixel, then write the value 0. So next is a grayscale image. So like here, as you can see, this is my original image. In the leftmost part, this is my original image, and like the pixels you can see clearly. Okay, so those pixels which are closer to black, their value is closer to 0. And those pixels which are closer to white, their value is closer to 255. So as you can see, like here, you can see my cursor, right? Like here, the pixels are white in color and their corresponding values are closer to 255. While like in this region, you can see that the pixel value is 0 or 1 or 12 because their intensities are very low. Okay, and these values are as it is jotted down in my NumPy array. So this is basically how you read an image in OpenCV. Okay, and next comes my RGB image. So in an RGB image, basically there are three channels of red, green and blue. Here you can see like this is my image and it has three channels, red, green and blue. So RGB image, unlike other images, it is stored in a 3D array. See, first divide this RGB image into three channels, red, green and blue. Okay, now treat this red image individually as a 2D numpy array. Okay, store this separately as a 2D numpy array. And like just like in the last image, what we did was if the value was close, if the pixel was closer to white, we stored 255. And if the pixel was closer to black, then we stored 0. Similarly here, if the pixel is so much red, then 255 is stored. The value is closer to 255 if the pixel is so much red, and if the pixel is closer to black, then a value closer to 0 will be stored. Okay, and similarly you do for your green channel. Like if a pixel is so much green, more your value is closer to 255. Okay, and same you do for blue. So three numpy arrays you just generate, and just then place them one after another, and these are your RGB channels. This is your 3D numpy array. So like here you can see like each channel has a 2D array associated with it, and when you just place them one after another, you get your 3D array. So here also the values of pixels are between 0 to 255. Now as you can see, like suppose I have this red channel over here, and when I store it in numpy form, then 0 to 255 were the values in my numpy array. Now if I again want to convert that numpy array into an image, what I can do is, like where the value was 0, I can create a pixel which is closer to black, and where the value was 255, there I can create a pixel which is white in color. So instead of red, you are using white. So here you can see that each channel can have a corresponding grayscale image also. So like you can see that these are my three channels of this image of a bird, and here you can see that the intensity of red is very high. So when I convert it into grayscale, then it's almost white in color. While in the green and blue channels, you can see that the green and blue intensities are very less, and it's almost black in color. That's why when I converted it into grayscale, then the central region, it's almost black in color, while it's not so in the red part.
Excuse me, Didi, I cannot understand that the previous slide. Why
This
it is in the
grayscale thing.
yeah, grace. Yeah, yeah.
See, suppose like you have an image. Okay, just wait a second. Yeah, this is your image, a plain red image. Okay, and what I'm gonna do is like, sorry. Um, okay, wait, just let me explain it in some other way. See, this is your red image. Okay, and you can see that if I split it into three, if I generate three channels out of it, red, green and blue, then obviously the intensity in the red channel is going to be highest, right? And the green and blue channels, they are going to have the lowest intensities, which means that they are almost black in color, and only the red channel is the most vivid and vibrant, right? And that's why inside my red channel, the pixel intensity is going to be closer to 255. That is the highest pixel intensity. While in green and blue channel, the pixel intensity is closer to 0 because there is almost no intensity of green and blue over here. So when I convert those images into grayscale, so like if I generate a numpy array out of it, and inside its red channel, the pixel intensities are closer to 255. And out of that numpy array, if I again generate a grayscale image, then those 255 values will be converted to white. Okay, and if I generate if I generate a grayscale image out of the green and blue channels, then there are the values closer to 0. So inside their grayscale counterpart, the pixel intensities are going to be closer to black. So that is what's happening here. See, this was my image. Let me just show it like this. See, this was my actual image, and you can see that if I concentrate on this middle part of this image, it's closer to red. So when I split my image into 3, R, G and B, then inside my red channel, it was most vibrant, most vivid. The central part, if you focus on, then it is mostly red. But since there is almost no green and blue part in the central part of this image, so this green and blue channel is almost black if you focus on its central part, right? So obviously the pixel values are going to be closer to 255 in the red channel, but they're closer to 0 in the green and blue channel. And if you generate a grayscale image out of their numpy arrays, then obviously here the pixel intensity was closer to 0, so this was almost black. This was also almost black. But here, since the pixel intensities were closer to 255, so this region turned out to be white. Now you got it.
Yeah, I got it. Means in that green one, if the central part is black, so turning into grayscale also it will remain black.
Yeah, yeah. But here, since the red part was vivid, so like um, uh, pixel intensity 0 in the red channel, it means so much red part, and in the grayscale image, it means like the pixel should be more white in color. So since here there is so much red and here it's so much white, so both of them are going to have pixel intensities closer to 255. While here both of these regions are black in color. So pixel intensity is going to be closer to 0 in both of them.
Okay, got it.
So you mean that the content of red is the highest in the central part of the image?
Uh, no, I'm saying that out of red, green and blue, the content of red is the highest.
Yeah, that's what I said.
Okay, fine. So yeah, now let's get into some coding part, like how you're gonna read the image. So CV2, like OpenCV was the name of my library, and while I import, then it's named as CV2. And CV2.imread. Imread is the function in which you pass the path to your image. Okay, and then it reads that image, returns a numpy array, and that numpy array is stored in a variable. So first argument, it's the required argument. You need to pass it. It's the path of your image. And second is a flag. This flag is optional. It can be 1, 0 or -1. So if it is 1, then this image is read in a colored format. And if it is 0, it's read in a grayscale format. And if it is -1, then the image is read unchanged. That is as it is. So let me just demonstrate it. See, yeah, here it was. See, cv2.imread. Then here is the path to my image. Okay, and see why I'm using R over here, that you'll see in a moment. Let me just print this array img. Okay, and it will throw an error, Unicode error. Why? Because inside this path you can see that there are some backslash characters, backslash u, backslash s, backslash c. D and \c. And there are some special / characters which are not treated as string but as special characters. Like for example, inside a string, when you pass \n, then you must know that it acts as a new line character. Okay, like let me just comment it out. Suppose I have a string where I pass this some random stuff. Suppose, yeah, this. And if I print image, so what it does is it just prints them in two different lines. So this \n, this thing acts as a new line character. So there are some special characters with \, and they are not treated as a usual string, but instead they have a specific function. So in order to avoid that, we place a R over here. R stands for raw string. So it just converts whole of this string into raw string. So you can see that this \u and \c, they are highlighted, which means earlier they were acting as special characters, but now they'll be treated as usual string characters. Okay, and now let me print this image. Okay, so yeah, this is my 3D numpy array which is printed. Uh, okay, and you can see that almost all the values are 255. It's because the image which I used, it was this image, and most of its part now it was white in color. So like what this does is it takes my first row and prints some pixels. Okay, then it skips some pixels and again prints the last pixels, and so it does like this for 3 rows and then for the last 3 rows. So what it does, it's printing the boundary values, and boundary values are almost white in color, so that's why it's printing 255. Okay, but let me use some another image. Red. Okay, so red.png, if I use, yeah, so here like different pixel values are printed, 0, 0 and 255, or yeah, just a second. Okay, so like this is yeah, the numpy form of your array, and it's printed. So you can see that inside this image variable, my image is stored as a numpy array. Next is I am show function. Okay, before that, let me just also show you the use of this flag thing. See, if I pass a flag of 0, no, then it will read this as grayscale image. So earlier you can see that it was a 3D array. It's a 3D array, right? But here it's converted to a 2D array because only single channel is there. Black and white channel or gray channel is there. Next is cv2.imShow function. What it does is when I have my image in a numpy array, so inside this image variable I have my array, then cv2.imShow function takes that array as input and displays it. So it needs two arguments. First is the window name and second is the source image in the form of numpy array. So window name is basically the in a string format you need to pass the name of your window in which you need to display your image, and here you pass the numpy array. So like this image I just read. So cv2.imShow, and this is the window name. So suppose here I am passing the window name and image. Okay, and I run it, but yeah, you can see that the image was there just for a fraction of second. Like you could see that a flash was there. Okay, but if I want my image to just be there for some time, then for that I need this wait key function, cv.wait key. What it does, it takes an integer as an argument, and that integer is the number of milliseconds for which I want to display my image. So suppose I pass 1000 inside it, cv2.wait key 1000, then my image is displayed for 1000 milliseconds, after which it disappears automatically. So suppose if I pass 1000 inside it, then my image is displayed for, yeah, he was not. Yeah, then my image is displayed just for a second and then it goes off automatically. Then cv2.wait key 0. 0 is it's a special argument. If you pass 0 inside wait key, then it will then your image will be remain there like until you close it manually. So if I pass 0 inside my wait key, then the image will be there until I close it manually. Okay, so this is the function of wait key, and cv2.imshow it displays your image while taking the numpy array as argument. Next is the cv2.imWrite function. So what it does is you just pass the name or relative path of your image and the numpy array. So what it does is it takes that array and saves it in your directory. Next is resizing and cropping. So like suppose I have an image over here, it resizes it. So basically it alters the number of pixels in it and hence it reduces or changes the quality of my image. And cropping, you all know like how to crop the image. So it's like how you do it in OpenCV. So this is the function to resize an image, cv2.resize. Inside it you pass your old image, then the new pixel values, like suppose initially my image was 400 by 400 and now you want it to be 200 by 200. So these are the new pixel values you need to pass, 200 by 200. So like suppose this was my original image and my new image equal to cv2.resize my old image, and suppose 100 cross 100 I need to pass. Okay, and this new image I want to display, so it's very small because the number of pixels are reduced drastically. Okay, so this is a way to resize your image by passing actually the number of pixels. Another way you can do it is
This is
this.
not cropping, no? What you
No,
did
this is not cropping.
previous.
This is not cropping. This is resizing.
Okay.
Another way you can do it is by scaling, like using this fx equal to 0.5 and fy equal to 0.5. So what it does is it just reduces the number of pixels by half in the horizontal as well as in vertical direction. So you can just implement it on your own and you can see that the pixel value just reduces by half and the image also, the size of the image is reduced by half. Next is the cropping part. See,
Is that
cropping,
0,0 is what it is? It will reduce from origin.
it's kind of an anchor point, like about what point you want to scale your image.
Okay.
Next is the cropping. So cropping, it's very simple. See, like I have my image. Okay, suppose it's 400 cross 400, which means that there are 400 pixels in the horizontal as well as in vertical direction. Now while cropping, like suppose I want to remove this text. Okay, so like my pixel starts from 0, like from the top left corner. So I just move some 50 or some 100 pixels down, and from here I need to start. So like my image is stored as a numpy array, and I can do is, what I can do is image slicing. See, my new image, what I can do is I can just select some values. So if I simply if I simply show my image, then it will show the whole image. But if I do slicing, then it will select some pixels out of it, just like we saw earlier in the numpy slicing part. So if I do like image 100 colon 300, what it does is it selects the 100th row up to 299th row, and it just displays only those pixels. So yeah, now you can see that the image is cropped because I'm displaying it only from the 100th row up to 300th row. And similarly, you can slice it in the another direction as well, uh, like this. Now the image is cut from its sides as well. So this is how you can crop your image. Okay, next is color space. So RGB color space is basically there are three channels in my image: red, green and blue. Each has some intensity. Like you all must have heard that you can generate any color out of some red, some green and some blue color. Okay, so you just take any pixel in your image and there is some red portion, some green portion and some blue portion. This is how your computers can easily read an image, but it's quite difficult for humans to understand it this way. So what we do is we use another format, HSV format. HSV is hue, saturation and value. So here in this diagram only you can see it very clearly that hue tells me what color is that, like green, blue, yellow, red or whatever. What color is my pixel. Then saturation tells me that how much vibrant or how much faded is my color, and value tells me how much black or white, see here you can see this value tells me like how much bright my color is, while the saturation tells me the vibrancy of the color. And to get a feel for it, you can just look at this diagram and you can just see what these HSV values represent. So again my saturation and value range from 0 to 255, but the value of hue, it ranges from 0 to 179. So this HSV format, it's easier for humans to perceive. Okay. And another
Maybe
is
that hue
B.
is 0 to 179 because black is not there.
No, actually hue represents the type of color, and if you want black then you reduce the value of value if
Okay.
you want black color.
What's the
Another is,
difference between saturation and value?
actually it's quite hard to explain it using words, but in this figure only you can see it very clearly. Like when you go along the saturation direction, the value of color increases, so it just goes from white to more colored. But when you go in this value direction, no, that color is there and this black and white thing, it changes. So it's hard to describe in words, but using this figure only you can understand it. Uh, yeah, and another is a Bgr color space. So Bgr color space is similar to RGB, it's just that it's inverted. So what happens is that like suppose this is my original image, and there are some inversions inside my computer due to which it reads this image in the Bgr format. So like you can see that in this image the intensity of red is very high because these are pink flowers. Okay, but what my computer does is it reads it as blue channel. So if there is high intensity of red pixels, no, it reads it as blue and it thinks that the intensity of blue color is very high. So this image is stored like this inside my computer. It just switches the red and blue channel. So this is yet another format, a BGR format, and this is HSV format. So you can change these color spaces in this in your using this code as well. Like your cv2.cvt color, this is the function you require. So you pass your old image and then the flag. flag is to convert the color space. So there are a lot of flags, like since there are a lot of channels, so Bgr to Rgb, Rgb to Bgr, Bgr to HSV, HSV to Bgr, HSV to Rgb, a lot of flags are there. So in like whatever conversion you want, so you can do using that flag. So like suppose I have this image and I have my new image as cv2 dot cvt color. Then inside I pass my old image and then I pass the flag. Flag is suppose I need it from Bgr to Rgb. Okay, and when I display this image, then this schemes is blue in color now because the red and blue channels are inverted. So the color space is changed altogether, like all the color spaces is changed. Yeah, next is analysis and processing. So now this is all about how you read or display an image. Next is you want to do some manipulations in your image or just play with your images, like what all is there in my image, detecting some shapes or something. Okay, so for that it's preferable to convert your image to binary. Why? Because there's less information stored in binary images and it's computationally efficient. Okay, but you need to keep in mind that while converting your image to binary, you lose a lot of information. Okay, because binary images store less information obviously. Okay, now there are two techniques to convert your images to binary. First is thresholding and second is masking. Thresholding, it's a way of converting grayscale images to binary. You generally use it for grayscale images, and colored images are converted using masking. So I'll be explaining thresholding first. So first is a simple thresholding. So this is a black and white or a grayscale image in front of it. Yeah. So this is a grayscale image and I want to convert it to binary image. So for that, first we use simple thresholding. See, the upper one, it's just simple thresholding. So it just gives pretty good results. And second and third, these are adaptive thresholding. So it's a much more advanced thresholding technique. So obviously it gives better results. So first is simple thresholding. So the syntax for it goes like this: cv2 dot threshold, and here you pass your original image. This is the thresholding value. So here what we do is, see, it's a grayscale image. It's a grayscale image. So obviously the pixel values are from 0 to 255. So in simple binary thresholding, what we do is we just select a global threshold value. Suppose I select 127, suppose. So what it does is all the pixel values which are greater than 127, it converts them to 255. And all the pixel values which are less than 127, it converts them to 0. So basically 127 pixel value is going to have some intensity of gray color, and all the pixel values which are darker than that, they'll be converted to black, and all the pixel values which are lighter or whiter than that, they'll be converted to white. Okay, so it helps in reading the image more clearly. Okay, so that global thresholding value that you need to pass over here. So here I'm just using 127. Then the next is the maximum value. So maximum value, like if a pixel is greater than 127, then 250 it will be converted to 255. And next is cv2.thresh binary. So this is a binary thresholding. Like cv2.thresh binary, this is the main function. What it does is, if a pixel value is greater than 127, it will convert it into 255. Otherwise, it will convert it into 0. And there are other flags than other than thresh binary as well. We'll see them later. So
Didi, that we
Yes.
have to assign 255 or means if we will not, we will assign 250 or 240, then it will greater than 127, it will convert to that value.
Well, let's just.
No, you cannot put any value above 255, but it's your choice whether to choose the range. That is, here we have given a particular range, right? So you can choose 127. Here we have chosen 127 to 255, or else you can use 0 to 10 or 0 to 100 or 100 to 200. It's your choice, depending upon which
Okay, there
value
is
you
a
have to
range.
threshold. Yeah, you can choose the range depending upon your necessity.
So means if suppose 120 to 130 range is chosen, then what it will happen?
It depends upon the image you use. Like, let's see while implementing.
Like if any such doubt comes now, then implementation is the best way. So suppose I pass 50 and then 100, cv2 dot thresh binary, and the image which I am using, it will be a grayish or blackish image. This is the image which I am using. Okay, gray.jpg. Yeah. So here you can see that 50 and 100. So like pixel values were converted to 255 because this is the darkest pixel you can see. But all the pixels, they are not converted to white. Instead, they are converted to some shade of gray. So,
Yeah.
which means, yeah. Uh, okay, so I'll just, search this, the exact function of this argument, and I'll get back to you.
Okay.
Okay. So, let's now,
Soumya,
let's,
I would like to interpret.
yes.
So इसका मतलब ये हुआ like if you have passed 50 and 100, so all the pixel values which are greater than 50 will be converted to 100, and all the pixel values which are less than or equals to 50, they will be converted to 0. So if you have seen in this
Okay.
image, Soumya, gray.jpg खोलना.
अच्छा हाँ एक्चुअली हाँ यही हुआ था वो एक्चुअली आई वाज कंफ्यूज बिटवीन 0
हाँ
एंड
कोई ना, वो तो
255
हो जाता है.
हाँ
सो जैसे जो भी पिक्सल वैल्यूज, ऑल द पिक्सल वैल्यूज व्हिच आर ग्रेटर देन 50, लाइक इन दिस कॉर्नर्स दे आर ग्रेटर देन 50, सो दे आर नहीं, उल्टा हुआ है
दे आर
ना, हाँ
लेस
तो
देन
उल्टा
50
हुआ है, हाँ
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 वही
सही है, दे उल्टा,
दे
दे
आर
आर
लेस
लेस देन
देन
50,
50
so they are converted to 0, and all the pixel values which are greater than 50, they are
ग्रेटर
converted
देन
to
100
100. So 100 is
या
some shade of gray, so they are converted to this shade.
0 means black. Okay. Okay.
Yeah, yeah.
या 0 मींस
Okay.
ब्लैक
Yeah. Yeah.
actually I was also confused in this. Okay, so this is thresh binary. It just uses this simple technique. If a value is greater than this threshold value, it converts it into 255, otherwise 0. Now you have some other techniques as well. See, like I have this simple Sudoku image and I applied this thresholding over here. So it just gives me this dirty result and I obviously don't want it. So this global thresholding, it poses such kind of problem. Uh, and we have some other binary thresholding techniques as well. Like they are not techniques, like they are just like how you want to threshold your image. See, thresh binary inverse, like earlier I used cv2.thresh binary. Okay, you can also use cv2.thresh binary inverse. what it does is it just gives me the exact opposite result of cv2.thresh binary. So like here you can see this is my original image and it has shades from black to white. So when I applied binary thresholding and this central value, I selected it as my thresholding value. So all the pixels which were darker than this, they were converted to black, while all the pixel values lighter than this were converted to white. And if I have my binary image now, then this binary inverse image is just the exact opposite of it. Like all the pixel values which are black here, they are converted to white here and vice versa. So uh, like yeah. Um, okay, it's because I have selected 50 as my threshold. So 127, if I select it as my threshold, so this is simple cv2.thresh binary. So the pixels which were uh, darker than 127, they were converted to black. Otherwise, it was converted to white. Okay, but if I do thresh binary inverse, oh sorry, yeah, if I do thresh binary inverse, then the result is just exact opposite. The pixels which were white earlier, they are now black and vice versa. Okay, now there are some other types also, like this is truncated. So what it does is, if the pixel value is lighter than threshold, then it's converted to threshold instead of white. So like you can see that the pixel values which are in the rightmost part, they are very white, so they are converted to gray, while the pixel values which are to the left or which are darker than the threshold, they are just kept as it is. Next is 20. So what it does is it converts all the pixel values which are darker than threshold to black, while the pixel values which are lighter than threshold, they are kept as it is. And 20 inverse, it's the inverse of 20. So here the pixel values which are darker than the threshold are kept as it is, while the pixel values which are lighter than threshold are converted to black. So these are just various techniques of binary thresholding, depending upon your choice, whichever you want to implement. But in all these techniques, a global threshold value was there. So that threshold value, it's same for all the pixels in my image. And this gives me some unwanted results like this. So in order to avoid this, I use adaptive thresholding. Adaptive thresholding divides my image into small blocks. Okay, and for each block, it selects a local threshold for that particular block. Okay, and in order to select the threshold for that particular region, what I do is, see, in the adaptive thresholding also there are two types of thresholding, mean and Gaussian. So you just divide this image into small blocks, select any particular block and take all the pixel intensities in that block. Now in the mean thresholding, you calculate the mean of all those pixel values, and in the Gaussian thresholding, you calculate the Gaussian weighted sum of all the values. Okay, and after you calculate the mean or the Gaussian, then you subtract a particular constant from that mean or Gaussian, and that final value is going to act as the local threshold for that particular block. See, this is the
The
implementation.
Gaussian weighted mean means what?
गॉसियन तो आप सर्च करो गॉसियन क्या होता है, गॉसियन वेटेड मीन, इसको गूगल करना क्या होता है ये, मतलब जैसे मीन होता है वैसे गॉसियन अलग, गॉसियन का अलग से फॉर्मूला लगता है गॉसियन वेटेड मीन का, इसको गूगल करना समझ आएगा. Like earlier we were using cv2.threshold. Now we are using cv2.adaptive threshold. So here you pass your old image, okay, and then this is again the maximum value 255. Okay, now you can use either cv2.adaptive thresh mean or cv2.adaptive thresh Gaussian. and then you pass the thresholding technique. Like once you reach a particular block inside your image, inside that image, so inside that small block, what type of thresholding you want to apply. Like you have found the local threshold value for that particular block, and inside that block you can apply CV.thresh binary or binary inverse or truncated or whatever. Next you pass the block size. So block size is like if I've passed 199 over here, so it means that it's gonna divide this image into small blocks, each of which has a size of 199 by 199. Okay, and next is my constant value. So like inside our adaptive thresholding technique, we saw like you first calculate the mean of or the Gaussian weighted sum of all the pixels inside that local block. Okay, and from that value you subtract some constant value, which is going to act as the local threshold. So that constant value you need to pass as the next argument. Okay. Yeah. So this is thresholding equal to CV2 dot adaptive threshold. Then I pass my old image maximum value. Then suppose I'll use here thresh mean. Then the binary the thresholding technique, and just use CV2 dot thresh binary for our purpose. 199, let's keep it as the block size, and 5 the constant. Okay, and here I'm using another image because the implementation is easier to see here. See, this is the image which I'll be using. Okay, so yeah, and 0 means I'll be reading it in grayscale format. Okay. So this is how adaptive thresholding works. So it just, it's a much better way of thresholding instead of simple thresholding. So like here you can see this is that Sudoku image we saw earlier. Using adaptive Gaussian, it's thresholded like this, and this is adaptive mean technique. So this was how you can convert grayscale images into binary images using thresholding. And next is how you convert colored images to binary images using masking. So for that I'll hand over to Pranav. He'll explain how to do masking and the rest of the stuff.
Hello, is my screen visible?
Uh, yes.
Okay.
Yes,
So it's
it's
visible
visible
now?
now.
Yes. Okay, so yeah. So guys, I am Pranav Suresh from MNC Part 2, member of Aero-Modelling Club IIT BHU. So I will be taking on the presentation from now. So in the analysis and pre-processing part, we have first dealt about this thresholding, right? So what did we do in the thresholding part? It was the conversion of grayscale images to binary. Suppose that you have a colored image. Okay, so the colored image might be of a red, green, blue, etc., all those colors and shades of different colors, and there might be certain instance like that. So now you want to particularly identify a particular colored part of that image. For that, what should we do? Here comes the use of masking. So in masking, look at this image. So here we have masked a particular color. Like we have heard about masking the emotions, right? So if we tell that, what does it mean? a particular person does not allow certain types of emotion to come out, or else he would be like only expressing a certain bit of things, right? So that's the same thing that we apply here, but here emotions stands for the color part. Okay, so we will be masking the colors. So masking is done using the cv2.inRange function. So what does this function do? So the function will take an input image, that's the old image or any image that we have chosen. And also it will have a lower and upper limit. So what's this lower and upper limits? So here the image that we passed should be in HSV format. Okay, so it's a standard conversion that it should be in the HSV format, and the lower and upper limits will be the lower HSV limit and the upper HSV limit. Suppose you have to threshold a yellow color, so you will get the threshold for lighter yellow and you will get the threshold for darker yellow, okay, or more brighter yellow. So then we will input that and we will get the threshold. So let's see it in the implementational part. Okay, so here I have this image of jeans. Okay, so here we are going to first mask this yellow color of jeans. Okay, we have to mask this particular yellow color. Okay, so for that I have searched the internet. Like we get the color charts for RGB and HSV and all types of images. We get the color chart in the internet, and all these resources and the documentations will be shared in the end part of this workshop through the notebook. We will be sharing this notebook. And remember one thing, in Jupyter notebooks, we have separate columns, right? So we don't need to import OpenCV or NumPy everywhere in every columns. So if we run a shell importing that, it will be applied to all the columns. Okay, so we can run the columns in separate part by using this run button or using shift plus enter. Okay, so now back on to the masking part. So here I wanted to threshold this yellow color. So here I choose the lower yellow limit here and the upper yellow limit. And then I created a masked image using the cv2.inRange function. And initially I converted the image that I had, that's a jeans.png image, to image HSV using the cvt color function and using the conversion of Bgr to HSV. Okay, so you know that in OpenCV, when we read, it would be in the Bgr format. Okay, the image will be read by the computer or OpenCV in Bgr format. Now we have converted it into the HSV and we have created an image HSV. And then I passed on this HSV image to the inRange function. Okay, so then I entered the lower limit and the upper limit for yellow colored, and I am now going to show that yellow image. Wait a second, I will close that window first. And then I am going to run this code. Yeah, look at this. We got a color here and we mask the particular color. So this is a binary image which masks the particular color. So here you can see a lot of dots, right? So these kinds of dots here are called the noise in a particular image. That is the unwanted pixels. So in this binary image, we only needed the color, right? We don't needed that dots. So there are methods to avoid these dots, which I will be teaching you in the upcoming part. Okay, so now suppose that if I want to mask the red hat of jeans, so I will be entering this lower red part and the upper red. And then if I run the code again, I will be masking the red part. Okay, so it's as simple as that. Now moving on, I told about reducing the noise, right? So let's see, how can I reduce the noise? Yeah. So for this, there are the morphological operations. So suppose that you have a binary image like this. This is the original image. There are two types of morphological operations. One is the erosion and other is the dilation. So erosion, as the name suggests, like you have heard about sand erosion, right? So in sand erosion, what happens? The water washes away the sand. So suppose that here the white part is your sand and black part is your water. So the black part will be washing away the white part. So when it erodes, the white part shrinks down. Yeah. So the black parts become more and the white parts shrinks down. So what about dilation? As the eye dilates, yeah, as the eye dilates, the white part will be dilated. Okay, so now to implement these functions, we used for erosion cv2.erode function, and for dilation we use cv2.dilate function. So how to implement these functions? So these functions will be having three inputs. That is the image as normal, the image that we want to input, and then we will choose a kernel. So what's this kernel? So this kernel, like suppose that we have an image. Suppose that we have an image like this. Okay, so this is our entire image. So we will be choosing a kernel like this. Okay, so here I have chosen a ones kernel. Like, so if I choose the kernel that I showed in the presentation, like np.ones 55, this one. Okay, so it will be a 5 into 5 sized kernel having all the values 1. Okay, so here it will be having 5 ones horizontal and 5 ones vertical. Okay, so this will be the kernel. Later, when I apply the function, this kernel will move on to the image, comes here, later comes here, and like that, it will move on to the entire image. And then the function will be applied. Okay, so here I have chosen the kernel, and what does this iterations do? Iteration means how far do I apply each kernels. So depending on the kernel size and the iteration, the amount of white or the desired part we want to erode or dilate will be different. Okay, so now let's move on to the implementational part of that. And here we can see I have a image here. Okay, so I am going to apply an erode and dilate function to this. So here is my Linux image, and I have chosen a kernel np.ones55. You can use this argument or not. It's just UNIT8. So it's just it will only utilize the values from 0 to 255. That's the limit of our RGB or our kernel size. And I have passed this kernel into the erosion. So now I am going to print the erode function. Okay, so I have created the erosion image here. I am going to show it in the erode function. Okay, now let's see what happens. So this is the eroded function. So a lot of white pixels got washed away here, right? So what if I implement the dilate function? So I have passed the same kernel and the same iterations to the dilate function, and I have created a dilation image here. So now I'm going to print this dilation image. Okay, so see, look at this. The image that I initially had got eroded in the erosion part and it got dilated. The white part became thicker, right? So this is what erosion and dilation do. So how can we use this to,
Yeah,
yeah?
how the computer is knowing what we have to erode and what we not have to erode?
Yeah, that's the thing now. So here I have chosen np.ones. Okay.
Yeah.
So in if I use the zeros here,
Yeah.
it will be giving a different output. Yeah, it get inverse, right? what happens is we have to choose what, like here we have implemented the one. So one means that it's bright, like it's the white part and zeros is the black, right? So depending upon our kernel and the type of kernel we are applying, the erosion and dilation will differ. Okay.
Okay, means it is only for white and red, white and black. Other color?
Yeah, the basically we like the use of this is to eliminate the noise, right? So it's basically applied for the white and black color, but depending on the kernel size and the type of image, it can be also utilized for certain other images too. Or in grayscale.
If I had a question, Bhaiya, if that 5 into 5 is means the size is more than 5 into 5, then what it will do?
Yeah, I was about to implement that. Now let's see what happens. Okay.
Actually, it's just like a paintbrush. So, like it's a ones array of 5 by 5. So you have a ones arranged in a 5 by 5 format. So that's a paintbrush you can consider, and that paintbrush is going all over the boundary of my Linux. So if it's if it's the erosion part, then it will erode the white pixels, and if it's the dilation part, then that paintbrush will paint like a white. It will paint white paint all over the boundary.
Just like this, I showed it, right? So I have this kernel, it will be moving all along and changing the pixels. So I have implemented what you said here.
Okay, in the dilation means the it will paint that DV told. So how much thickness it will paint?
Yeah, I have changed the kernel size. Initially it was 5 and now it's done. So now the thickness changed, right? So how much thick will be comparative on how much thick the initial image is. Okay.
Okay.
So in a case you want to remove the noise, you can use the trial and error method here. So every image will be different, right? So how much you have to dilate, how much you have to erode depends on your image. Okay.
Okay.
So same applies with the iterations too. If I change the iteration number, the amount of erosion and the amount of dilation will also change. Okay. So to remove the noises, we can do one thing. Like for initially you had the image that like themes here, like here we have a lot of dots. So we can first use the erode function, and the erode function will remove all this white dots here. And if we apply the dilate function after that, so a little bit of unwanted white part will also be removed by the erode function, and it will be brought back to normal using the dilate. Erosion and dilation is the method to remove the noises here. Okay, so now let's move on. How to draw images in OpenCV. So suppose that you have a particular image and you can draw lines, you can draw rectangles, you can draw circles, you can even input text on them. So here, let's see how we can do that. So I have created an np.zeros image, like if I create a zeros image, like an image containing all the pixel value 0, what color it will be? Can anyone suggest? All the values are 0. 0 implies what?
Black.
Black, right?
Black.
So if I create an np.zeros function, all the images or all the pixels here will be black. So I will get an entirely black image. To this, I am going to draw a line. Okay, so let's see. I have created a function here, cb2.line. So what does this line function do? It will take an input image. Okay, so I have taken this zeros function, the black image, as my input, and it will take a starting point, the point from where this line must be drawn, and an ending point, point to which the line is drawn. And it will we have to give a color. Okay, so this will be a particular color. We can change this value depending on our choice and which color combination we need, and we can choose the thickness here. 1, 2, 5, 10, etc., depending upon how thick your line must be. And now see what happens to the image. Okay, so I have created a green line here. You can change the color or thickness depending on your choice and your needs. And now I am going to implement a rectangle function. So here, cv2.rectangle function will help you to create a rectangle. So just like the line function, we have to choose an input image. We have to choose a starting point, top left point, and an ending point, bottom right point. And we have to choose the color, and we have to choose the thickness. So what does thickness refer here? So initially, let me implement this function and then I will explain. Okay, so here I have used the thickness as -1. So -1 means fill the entire body of the rectangle with the color we have chosen. So suppose if I don't use -1 and I am using some value like 10, and I will get the thickness of the borders as 10. Okay, so if we enter -1, we will get a entirely filled image, and if we change the thickness to any other value other than -1, we will get the thickness depending upon the value we have entered. And now, what if I have to draw a circle the same way, but the input values might have a little difference, and I am inputting the same image here, and then I choose the center on which the center of the circle. So later I choose the radius. The third input will be the radius, and the fourth input and the last input, same as the last time, the color and the thickness of the circle that we have to draw. And now I am going to draw the circle, and I got a circle here. Okay, and now what if I have to enter a text here? Okay, so I am using this put text function here to input a text into an image. Okay, so here I have entered the input image, and then I choose the text value that I have to enter. Okay, so I have choose the OpenCV, and then I choose the place from which I have to choose start the text. So this is the text part, and then I choose the font. So there are a lot of text formats that we can choose. Like these are all the different types of text formats that we can choose in an image. It is available in the OpenCV documentation. The link to the documentation will be shared after the workshop in this notebook itself. So I have chosen the symbol font Hershey Text, and then I choose the thickness and the color of the font that I have to apply. So now I am going to run the function, and I got it. So if I change the font size or the color, the change will be appeared here. Okay, so we can also change the text. We can choose a value and assign to the text. That's your choice, but it should be a string. That's the only condition. Or okay, so now let's move on to a little bit interesting part of our presentation today, and that's the contours. So till now, the things that you applied comes in the basic part of OpenCV. So now let's see what more can you do. So what are contours? Contours are a curve joining all the continuous points along the boundary having the same color or intensity. So to draw contours with greater accuracy, we use binary images so that it could detect the edges more specifically. Suppose that you have a hand image, we first convert the hand image by thresholding or masking to a binary image, and then we apply the contours to it. So it could draw the particular edges, right? Here they have drawn in the yellow color, the edges of the hand. Okay. So how do we
Yeah, please
detect these
go
codes?
to the previous slide.
Which slide? This one.
Previous. Yeah,
Oh,
in that one. No, next.
drawing
No,
images.
next. No. In that contours, the first slide of contours.
This
Hand
one.
one. Yes. Yeah,
Okay.
here A curve joining all the continuous points along the boundary means which one is the boundary?
This boundary between the white and black part.
Okay, means in colored images we cannot distinguish properly which is boundary. That's why we have to make into
That's
binary.
thing now. To draw contours, we cannot use white images because it would be difficult to detect. So what we
Yeah,
do is we convert the white image to a binary image, then detect the contour points. So suppose that this is the same image. The first one and the second one is the same image, but first is colored and second is binary, right? So from the binary
yeah,
image, we get the landmarks, we get the points of the boundary, right?
okay,
So we
yeah,
use that boundary to draw in the same image.
okay, got
Okay,
it.
got it. Yeah, that's the thing. And now let's see how to detect these contours. Okay, so contours, to detect contours, we use the find contours function. So here we enter a masked function. That is, the mask function is basically the binary function. Okay, it should only have the white and black colors in it. And we use certain types of contour retrieval modes. That's a tree, and there are certain types of retriever modes in there. You can work on it and try it out in the documentation of OpenCV. But here we have choose a more accurate and more interesting retrieval mode here. And then comes the approximation method. So what's this approximation method? It's the decision, like we have two types of approximation methods. One is the simple and other is the none. So in the simple approximation method, it will only detect the corners. Okay. So in a line, we can detect, we just need 2 points. In a rectangle, we may need 4 points, like that. So in none, it detects all the points along the line. Okay. So it will be having all the contour points. These are the two types of approximations. And let's see, let's take an image and apply this function. Okay. So I have this shapes image here. Okay. So just like I have used the same function that I used in the chains. For that, I wanted to detect the yellow color, right? So I have used the same upper limit and lower limit, and I have applied the mask. In range, I have used the in range function, and I have created a masked image. So till here, you don't have any doubts, as it is already taught in the earlier part, right? So I have a binary image now. I have a masked image now, and I have to draw contours. I have to initially have to detect contours. Okay, so to detect contours, I use this contours function to find contours, and I have used the retriever method and the approximation method, and I got the contours here. And look at this. Here, we will get the contours as array. So look at this. Here we have two images. So we will be having two sets of arrays. Okay. The first set of array for the star and the second set of array for the image, or vice versa. It will be dependent on the computer which array should be belong to which one. That I will show how to detect this. And so I have detected the contours. Okay. Now I want to draw the contours into the image. So what should I do? To draw the contours, I use the cv2.drawContours function. In this, we will be inputting an image, and we will be the contours which we extracted using the find contours function will be passed on to it. And if we enter the -1, it's the index of contours. If we enter -1, all the contours of all the shapes will be shown here. And then the color of the contour lines that we have to draw and the thickness. Okay, so now let's implement the draw contours function here. And yeah, I have created a copy of the image. So here I cannot draw the image in the same image itself. So I am creating a copy of the image that I have to draw. And now the image dot copy function will just copy the image to a certain another image. Okay, so these both are the same one, exact copy of the image. Okay, so now I am utilizing this draw contours function, inputting this image one as my input. I have taken the contours from here, and I want to draw all the contours that I have. So I have chosen the -1 and then the color and the thickness, and let's see what happens. Okay, so this was the original image. I masked it. From the mask, I detected the contours, and from the detected contours, I have drawn this one. Okay, so the yellow colored images or the yellow colored shapes are contoured here. Okay, so if I want to draw individual contours, here I drew it for the star and the other shape. So now I don't want to do that. Okay, I just want to draw it for a particular shape only. So here I got two types of contours, right? So if I surf here, I can see that this shows the ending of a single array. So here is one. And now when I go to the lower part, so yeah, this is the ending of the second array. So I am having two sets of contours. So what should I do now? I don't know which one is the first or which one is the second. So I'm just entering. The indexing will always start from 0, right? So I'm just choosing the 0 and I am going to draw it. So here we can see that when I choose the index as 0, I got this one. Okay, this shape was contoured. So the 0 index will be belonging to this shape. And if I change it to 1, I will be getting the star. So 0 belongs to this one and star belongs to this one. Okay, now there is another method also to detect the contours function. So how's it? So here I have all my contours, right? So now I just want, if I want to detect the 0th one, I can even change this -1 to 0. And then I will get the, wait a minute. Okay, so this have to be removed then. And if I run it, yeah. If I run the same function, I will be contouring the first shape. Okay, so we can choose the index here by choosing the values for the contours, or we can change the second value and choose the index, but don't do both on the same time. So if we are changing the this part, the contours one, you should not change. This should be kept -1. And if we are using the contours itself and you want to choose the image or the shape, you can change the index or the index of the contours here. Okay. So now going back to our presentation. So these are the things that I explained now, the two methods to choose the contours. Okay, choose the contours individually. So that's explained in the slide, and that's all. And now let's see, there are a certain sort of features for the contours. So in physics, what does moments mean? Come on, guys. What does moments mean in physics? So what's moments?
Displacement of any particle.
No,
Moment
moments
about
are
an
x m cross x, m into x.
Okay. So what does moment about an axis mean?
Yeah, r cross x, I suppose.
Torque.
Torque.
So basically, moments about an axis means the distribution of the weights, right? If you take into kinematics and all, it's the distribution of the weight about a particular axis. So if we take an image, where will be the axis or the origin of the image be? We all know about it. where will be the origin of the image be? So
It depends upon us.
no. Like initially, the computer takes the origin of the image as the top left part. Okay. So what does moments in our computer or the image sense means? It's a weighted average of image pixel intensities, and we can get the centroid or spatial information from the image moment. So to find the moments of the image, we use this function here, cv2.moments function. We get the moments. So what does this function do? So to this, we have to enter the contours. Okay, so in the previous example that I showed in Jupyter, I showed that there was this star shape, right? So if I am entering the index of the star to the contours function, and then inputting it in the moments, then I will be getting the moment of that particular shape. Okay. So what all things can we do from this moment? We can use it to calculate the centroid, that's the center of that shape, or we can use it to find the area of the shape. There are a certain lot of kinds of functions for that I will show you in the next slide. So now let's see what these moments do. Okay, going back into the presentation, into the Jupyter. Uh, okay, so we have to detect an moment of the image. So I have this contours function here. I have taken the contours and like I have copied the image and I have drawn contours to that. And initially, it's the same image, like the colored shapes that I showed you. Right, it's the same image, and if I draw contours, I will be having both this, and this will be index 0 and this will be indexed 1. Okay, so index 1 means this star shape. So I am transferring all the star images to this contour function. Okay, I have taken the contours of the star to this function C and T, and I am entering that particular contours of the star to cv2.moments function, and this function will extract the moments of that particular star. Okay, so now after closing this, I have printed it. I have printed all the moments. So the moments function will take out this much of values. So what's this M00, M10? I will explain it. So to find the coordinates of the centroid, yeah, this documentation consists of what these moment functions do in the mathematical part. So to find the centroid along the x direction, we have to choose the intensities of the x part and divide it by the total weight. So M00 means the total intensities, total number of pixels. That's the total weight of the image. And M10 takes out the weights in the x part. So by that, we can find the centroid in the x part, and using the M01 by M00, we get the centroid in the y part. So we get the x and y coordinates of the centroid. And if I used it to get the cx and cy, the cx will be the centroid of the x coordinate of the centroid, and cy will be the y coordinate of the centroid. So now I am just going to depict the centroid. Okay, so I have used the cv2.circle function. I have inputted the cx and cy, and have choose the, like I have explained the input formats, right? I have choose the radius, I have choose the color, and it's a completely filled circle. Okay, and now I am going to run this one and see. I got the centroid of this shape here. Okay, so at the same time, if I use 0, I will be getting the centroid of the other shape. Look at this. I got the centroid of the other shape here. So depending on the image that you want to find the centroid, you can change the values. And if you want to get the centroid of all the images, you can use a for function. You can use a for loop and put these values inside that, incrementing on the indexes. Okay, so what if I have to find the area? For that, I have this function. So yeah, let me show the presentation and later I will come back to that. Okay. So using the contours, we can find the area, we can find the perimeter, and there are a lot of certain stuffs that we can do. Okay, so the contour area is given by the function cv2.contour area. And just like that, for the shape, we have to find the area. We enter the contour index of that particular shape into this function. And for this, as the same thing that we did here, for the perimeter also, we enter the particular contour index value of that particular shape. And there is this flag here, true or false. So if the shape that we choose is a closed shape, that is, it's a closed circle, or the image that we choose there, like if it is a star, it's a closed figure, right? So if it is a closed figure, to find the perimeter, we use the true function, true flag here. And if it is a open figure, like it would be a arc, right? It also have a particular length. So to find the length of the perimeter of the particular arc or thing, we use false here. Okay, so now let's implement the thing. And here we have this print area function. Use the area contour area function to get the area, and now I'm going to print that area. Okay, so have to close this first, then only it will print. Yeah. Okay, so I have got the area of the particular shape I choose here. So initially I have choose the 0, so it will be the this right bottom shape. Okay, so if I want the area of the star, I would be using this this index. That is, I have to use the 1, and I will be getting the area of the star. Okay, so now let us look at how to draw bounding boxes around certain shapes. Suppose that if I have a shape like this, if I draw a box around the shape, a green colored box, look at this. So this is called a bounding box. So to find the bounding rectangle, we can use this contours itself. So there are two types of bounding rectangles, and first let's come straight into the straight bounding rectangle. So it is a straight rectangle and it does not consider the rotation of the object. So suppose that if it is an inclined figure like this. So if I want to use a straight rectangle, it will be having a lot of unnecessary areas, unnecessary regions counted by it or bounded by it, right? So it will be a little bit large, and it will the area of the rectangle won't be minimum. And I can also use a exact bounding rectangle, minimum area rectangle, which bounds all the area in a particular perfect way. So for the first part, to draw a normal bounding rectangle, I use the cv2.bounding rectangle function. So it will get the x coordinate and y coordinate of the starting part, top left part, and it will also get the width and height of this rectangle, width and height of this rectangle. So by that, I can use the cv2.rectangle function to draw the rectangle. I will get the top left part using the x and y coordinates, and the x plus w and y plus h will give the bottom right part. Okay, and to draw the minimum area rectangle, we have the cv2.min area rectangle function. To that, we will enter the contour value, and it will get a function. It will get a value here. So by the we will get a value, and we have to pass the value to the box points function, and it will create into x, y, etc. coordinates. And I will explain further while implementing. This might be a little. Okay, so here I have this Rubik's Cube image. Okay, have this Rubik's Cube image with me. And I have found the I have used the same thing. Like I have masked the yellow part of out of this image. I have detected the contours from this image, and now I have drawn it. So now I have to draw a bounding box around this rectangle. Okay, so what should I do? So I have found that for this rectangle, the index value is 2. So I have to draw a bounding box around this rectangle. So I am doing like, I have detected the contour value here and I have passed the second index to it. And now I am using the bounding rectangle function to extract the x coordinate, y coordinate, and the width and height of the rectangle. And now I am going to draw the rectangle around. Okay. So yeah. See this yellow rectangle that I have got here. So I have drawn this green part already using the draw contours function. I have drawn all the contours, and now I have created a bounding box around that image. So what if I have to create a minimum area rectangle? For that, I use the minimum area rectangle function to find out the rectangle values, and box points will create it into a normal readable part. And then I have to make sure that it's an NP array. So I have used this np.int0 to convert it into an NP array, and now I am drawing contours using the same values that I got there. And now let's see what that shows. So look at it. There a red box applied is present now, right? So it's exactly tilted in the same way as the image I had here is tilted. So it will be containing all the pixels with the white color there. It will be exactly bounded to the image. So now let's go on to the second last part of our presentation. Okay. So contour approximation. So while I applied the last example, you can see this was a cube. Okay, so all these blocks had to be exactly in rectangle shape. So, but I got a different shape here. Like the contours were not perfectly in the shape I wanted it to be. So what should I do? It's because it detects a lot of points. Okay, it detects a lot of contour points, and when we join these points, it might get a little bit shaky here. So to approximate that, we only need these endpoints, right? We only need the corner points. For that, we use the contour approximation function. So what does this contour approximation do? Okay, it approximates a contour shape to another shape with less number of vertices depending upon the precision we specify. So we can change the precision. To understand this, suppose you are trying to find a square in an image. Yeah, the thing that I stated. We have a bad shape and we have to make it more precise. So this is the way that we choose here. So we choose an epsilon here. So here the epsilon is created by multiplying the arc length of the contours here. And then I will pass this epsilon value to the approx poly dp function. So what this will do, like here, if I draw an initial contour around this shape, it will be getting a shape like this. So shape like the right one. Okay, so I don't want that. I want the exact shape. I want the exact contour. I have to get a bounding box exactly in the shape of a rectangle, so that I apply this approximation function, and it will reduce the number of contour points that I already had. It will only get in more relevant points, and it will help me to draw a particular rectangle there. Okay, so suppose that this is the original image. If you choose the epsilon 5, it will little bit reduce the contours and it will get a more shape like this. And if I increase the epsilon value, it will get more cornered, right? So in the rectangle, I needed more cornered rectangle to be a perfect shape like a rectangle. I have to reduce the curves of the line that I drew, right? So if we apply the same thing to a circle, the curve will be reduced to more cornered shape. Okay. So now let's look at the implementation. And yeah, so I have used the same Rubik's cube that I had here. I have choose the index of this block of the cube. And now I am going to use the approximation of the contours. I have created an epsilon with an approximation of 0.1, and I am using the approx polydp function to get the approximated contours out of this. And now I'm going to draw the contours on a copied image that I had. Okay. So close this. Wait a minute. I haven't showed the approximated image. Yeah. Okay. So this was my initial image. This was the problem that I had here. The lines were a little bit more curvy, right? It was like a lot of curves were there. So while I approximated, the curves got vanished and I got a little bit more perfect shape. But there's a problem here. If we change the value of this epsilon in a way we like, the output that we get might become different. Okay. So if I choose 2, it will approximate more. It would be a wrong approximation, right? So we have to keep a limit, and we can find the limit by trial and error method itself. So we don't know how the contours are detected. So we have to try certain values and come up with a more accurate value for the epsilon part. Okay. So now let me show you one thing. Like using this approximation and the contours, we can detect certain types of shapes. Okay. So in a body, we have certain circle, square, etc. So if we want to detect what shape is the which figure, so we can use the approximation. So I have created a simple implementation. So let's see what that's. And I have this simple.png, and I have created a simple implementation. I will be sharing this code with you. So look at this. So this was a simple image on which we can do the approximation simply. But there is a problem. If I use some other kinds of image like I had here, the colorful shapes.jpg function, JPG image. So if I use the same image here, let's see what it will bring down. Oh, that's something serious, right? So what I am going to assign you is a task. Okay. So here there are a problem, like if the geometrical shapes were not critically analyzed, because if we approximate the contours, it will still have a lot of points extra to it. Okay, so we can always rely on that method to find the shapes. So suppose that if we want to recognize a circle, we have certain functions like area by perimeter square is a constant that equal to 1 by 4 pi, right? For rectangle, square, triangle, and all the figures, there are some sort of mathematical functions which is unique to these figures. So what you have to do is you have to detect these functions and implement these functions to exactly detect the objects. So we will be sharing assignments for that, and you can do that in the assignment part. Okay. So now let's move on to the last part of the presentation. That's the video processing. So just like the same way we did for the images, we can also do for the videos also. All these functions that we applied here can be, we can just directly apply to the images. But like here, if we enter the values as image, we have to choose the video function here, and we can pass the video to all these functions, and we will get the exact same thing with a live output. Okay. So here the frames will be in Bgr image or grayscale or binary, just like the way Soumya explained to you in the image part. So moving on, what does video processing do internally? So what it does is that it takes a video and it reads the video. So you all remember the old old school projector, right? The one that were used certain years ago. So it had these films in it. Okay. So same as that, we will separate the video into separate films or separate frames and do the processing on these frames individually, and we will combine all the frames and give an output out of the frames that we created or manipulated. So to capture a video, you need a video capturing object. So in the computer, it can be a webcam, like you are seeing me through the webcam, or else we can use a pre-recorded video, MP4 file, or there are a lot of formats for the video, right? So you can choose that kinds of files, and there would be a argument, can be either a device index or the name of the video file, and we can use this video capture function to capture a video. Okay, so now let me show the implementation of the video processing part. So here I have a test.avi video. So yeah, here I have this test.avi. That's this video, and I am going to read the video using my OpenCV function. Okay, so I have entered the video capture function, and I have entered the video here, and now I am going to play that video. Okay, so this is the video, and we can change the speed of the video by changing the wait key function. Okay, if I have used 30, if I am using 300, it will get a little more slow, like that. Okay, so suppose if I want to record my own video, I have to use the camera for that. Okay, for that I have to enter 0 for the video capture part. So if I enter the 0, I will be getting the live input of my camera here. Okay, so this is me, and you can see me directly through the video, and it's little bit lagging because I choose the 300 here. If I choose one, it will be exactly the same way that I need it to be. Okay, so yeah. So yeah, that's the live video output that I got from my webcam. And same way as we applied all the functions to the images, we can apply the thresholding, we can apply grayscale, we can apply all the things and get the video in the way we like. So I'm just going back onto my live cam, and I am applying the thresholding and things, and let's see what happens. So this is the grayscaled image. This is my original video in output. I just grayscaled it, and now I just threshold it. I gave the output, and in the same way, all the functions, you can do it in the video part also. So here comes the end of our learning part, and these are the resources that I utilized here. As you asked, yeah.
Can you please explain again the video processing? A little tough to understand.
Okay. Yeah, so just went a little bit fast because the time limit has exceeded, and because here, look at this. So here the cap, just like yeah. Okay, so here CV2.video capture will get the input and pass it into a variable. Okay, so now I am using the cap. While cap is open means that if the video is being read, if the video is being read from a file, or if the video is read from the live camera, I will use the while cap is open. So if it is 1, it means it's true, and the while function will run. Okay, so inside the while function, I am using this while loop because it's not just a single image, right? I have to repeatedly do this so that I could show all the frames. Okay. So here, later I am using the cap.read function, and it will give two outputs. The frame will be the frame on which the image is present, and red will be is the video running or not. That shows the red function. So if the video has ended, I have to stop the playback. So I use if red is equal to false, it means that video is ended. I have to come out this while loop. I have used the break function here. Okay. So I have to this CV2.resize function, just the way I resize the frame. I have to use this resize function, and these three parts are already explained, right? You all know about it. Okay.
Yeah,
Till
yeah,
here, yeah, all this part you know, like till here, all this you have understood all the functions above, and you know about this much things. Now let's see what if CV2.wait keys. I have explained the wait key function, like it controls the speed of the video playback. Okay, so what's this OXXF ORDQ? So there is a problem, like we cannot stop the video playback just like that. So suppose that if I create a video and if I am reading a video and I am trying to close it, it will not close that easily. Right. Yeah. So if I try to close it, it will not close. I cannot close it like that. If I implement in OpenCV, I cannot close these windows just by clicking on the close button. If I am playing a video, so what should I do? I should use a particular key. So I have chosen this Q. So what is this is that when I press the Q button on my keyboard, the video playback will be stopped. I run the function, it reads the input from the video. When I press the Q, it gets stopped. Okay, so that's the OXF ORTQ function. And just last thing is like cap.release and destroy all windows are the general functions we apply to initialize the running of the part. And that's all. Got it, right?
I got it.
Okay, so here are the resources. I am sharing a YouTube playlist in which you will be getting a lot of in-depth knowledge about OpenCV, and it also contains certain simple projects that you can do in OpenCV. And here's the NumPy documentation, the RGB and HSV data files, and the thresholding, the morphological operations, drawing functions, contours, implementation of the contours, image analysis, image moments, structural and shape descriptions, and all. Okay, so that's all with the resource part. And by that, I am finished. And is there anyone who is going to say, I have doubts? You can ask now.
Here, this all will be shared, Bhaiya.
Yeah, this will be shared. The recording along with this will be shared. I will be uploading it in the GitHub and sharing with you. And I will be also sharing these files. Like I have a lot of files like this. I have a lot of images like this on which you can play upon. You don't need to go to the internet and search for all these things. I have created a simple file dictionary here. And regarding the IDE you want to use, you can simply use any IDE, VS Code, or any IDE which you like. And I will always suggest if you are using Python, it's better always to use Jupyter Notebook or our Google Colab. Yeah, the last Python workshop, Utkarsh did it on Google Colab, right? So just like that, because